so the plan for today is, we'll start in 1 minute, but was to build the idea of ensembles. Well, before I go to that, let me say many of you, not all, but quite a few send me emails saying, Professor, I could finish the homework, I need a couple more days. I am okay, so take a couple more days. But I believe that with the material I'm going to give you today, which essentially I hope to finish chapter 2 in the book of Kittel, or I don't know which chapter in the book of Randell, I will have a few more problems to give you. So don't take this as a habit and try to finish them, because I will very soon give you a few more problems, okay? Based on these ideas of ensembles, which we are going to launch ourselves today. My thought would be perhaps even to start discussing a little bit of kinetic theory. We'll see. So I'll briefly remind you what I said about ensembles next time, and today we are going definitely to develop it in much greater detail. Okay. Here. Okay, so the idea is, I reminded you that one of the great ideas of Gibbs, and then Boltzmann developed it more in ways that we will discuss later today, was the idea that we cannot follow in time what's happening with the system, because the system is fluctuating a lot, but what Gibbs sort of surmise is that the system will in time go through every single possible of all the microscopic states, such that they are compatible with the constraints of the system. For example, last time I mentioned, if your system is isolated, the energy has to be whatever it is, E. So any state of the system that has a different energy, the system cannot go into it. But among all the states that happen to have the same energy, the system is as likely to be in any one of them and will visit all of them. So when you are calculating or measuring or studying some quantity, you can do the following operation: replace the actual physical system by many copies of the system, which are in all the different microscopic states that are consistent with those constraints. And you replace doing a measuring or calculation of the system by calculating and doing an average over your ensemble. And in the case we are discussing now is the simplest of the ensembles. Hopefully by today's class or at the beginning of this class we'll present a more realistic in certain aspects ensemble, which describes better the real world in which systems are not isolated and are normally in contact with something. But for a system that is isolated, the consequences of this are very simple. If the degeneracy of the system is some number G, we assume that the system is as likely to be in any of the G systems, and that means that the probability we assign to each of them is 1 over G, because they are all equal. So I was saying, if we know that our energy is such that our system had the number of spin up minus spin down was just 1, well, there are 10 combinations of putting 3 arrows up and 2 arrows down, which is the combinatorial 5-3, 5 factorial over 3 factorial, 2 factorial, okay? So 4 times 5 over 2, 10. Okay, there are 10 combinations, and the system is as likely to be in any of them, so I would assume that there is a group of 10 copies of my ensemble, each one has probability 1/10. Or if you want to put 50 of each, well, but the fact is that you put them all in the same proportion, because we assume that the system is as likely as being in any of them. And your statistical analysis of whatever it is that you need to study is based on this statistical problem. So you forget about the real system and you replace it by a statistical analysis on this ensemble. And I mentioned that this presupposes something that not always needs to be true, that every single possible microstate of the system can be reached. I said there are example systems that are in the physics of glasses particularly. Systems can be frozen and certain states are frozen out and the system can never go to them, so then you cannot include them in your average because then you will get nonsense. So there are certain practical limitations that you have to study when you build your ensemble. But in the most general case, certainly in this case of spins that we were discussing, we assume that this state or these states are equally accessible to the system, so we all put them there with the same probability. I mentioned that if you are studying the energy such that you have 5 spins pointing up, well then your ensemble is made out of one element because there is only one way of putting 5 spins up. The combinatorial 5-5 is 1. Well, it's not too much of a statistical ensemble, but whatever it is a characteristic of systems that have a maximum possible energy or a minimum possible energy that at both ends of this spectrum normally you have very few states. For example, there is only one way of putting 5 spins up or 5 spins down. In realistic systems, when we will discuss the distribution of molecules of air in this room, the velocities of the molecules in this room, well, there is no maximum, there is only a minimum because the minimum speed a particle have is 0, but there is no maximum, so we will not find this funny fact that for certain particular constraints of the energy we get just one. But that's a detail. The general philosophy is what I explained last time, and I want to use it today to show you that although there are many states of a system, so now let me start with this. This anymore, this was just to show you. We can use this idea to show that the system is very likely in one of those possible ones, and using the idea of an ensemble we can determine a lot of the statistical properties just by looking at what happens when systems interact between themselves. And we will use first to motivate the thing, the calculation using up and down spins as we have been using now, but then I will generalize it to get the idea of entropy, temperature, etc., and all the quantities you know and love from classical physics. So actually what I have in mind, just to fix ideas, will be that I have two systems, 1 and 2. One has N1 particles and energy U1, the other has N2 and energy U2. Each one is distributed in some way that I know in detail. For example, if these are spins, we already discussed which states are more likely, which states are less likely, and now we put them in contact. And in such a way that they are in contact, so the energy can flow from one to the other, but the total system is isolated. So U1 plus U2, which is the total energy, will have to remain constant.
What is U?
Pardon?
U?
The sum of the energies of the two systems.
Oh,
Yeah. So we will assume that this is isolated. So we will apply our theory of an isolated system to this, but allow the possibility that energy can flow between them and see what does it mean. So to and we will start with a system of spins, but then we will generalize it. So imagine that what I have, my system 1 here has n1 spins that can point up or down, and S1 is the excess spin, as we discussed before. The number of spins up minus spin down over 2 in one system. But remember, the energy is directly connected to this number S1. And the other system will have N2 spins and will have S2 as the number of excess spins. And this can be two different systems. One can be 50 times bigger than the other. I am not making any assumptions about the numbers S1, N1 and N2, and S1 and S2. Except the obvious, S1 is the number that runs, as we know, between minus N1 over 2 and plus N1 over 2. The same is true from the other one. But there might be some residual interaction between these spins, so that might make some spins flip. But what will have to be true is, because the total energy is constant, remember, the total N is a constant, it's N1 plus N2. The spins are not moving, so we assume that this is a fixed number. The total S is obviously, the total S is S1 plus S2. If this has 30 excess spins and this has 20, the total system has 50, okay? So this is true, and the energy U1 is a function of S1, as we discussed. It's minus, in my simple example of putting a magnetic field, was minus 2 MB S1, and the energy of state of the system 2 will be this. And since the sum of the two energies is constant, we have that minus 2 MB S1 plus S2, this is the energy U1 plus the energy U2, must be a constant. In other words, what I am saying, that S1 plus S2 has to be a constant. If here 5 spins flip in one direction, here 5 spins will have to flip in another direction, because the total S, the sum of S1 plus S2, cannot change, because this is isolated. Yes?
So you consider that flipping more spins does not correspond to investing more energy to flip them?
No, because each time a spin flips here, the energy goes down, and the spin flips here, the energy goes up. As long as S1 plus S2 is constant, the energy will be constant. So, if some spins flip here, the energy of this system will change. But so will the energy of this, so that the sum is constant. Because I am assuming that they do not interact with the outside world, so I am not pumping energy in any way. That's what I'm doing for the time being. Later on, we will consider what happens when energy can come from the outside, but not for the time being. So I want to study this situation and study the statistics of this as these things flip around, but in such a way that the number, whatever initial value S1 have and initial value S2 have, the sum has to remain constant. So you see, what we can say is the following. What is the number of states that the system has? Well, if this can be in 10 different states and this can be in 50 different states, the total possibility is the product of this times this, right? So the total number of states will be G of N1 S1 times G of N2 S2. It's a simple product because these are two different systems, and for each state of this can be in some other states, etc. So, but with the condition that S1 plus S2 has to remain fixed as a certain number S, which is given by S1 initial plus 12. The system is characterized by a value of S, so any possible configuration will be given by G N1 S1 times G of n2 s minus s1. These are the only possible configurations because s2 has to be such that s1 plus s2 is the constant s. Okay? But besides that, s1 can be anything because I said things can flip here as long as others flip here so that to keep this number constant. So there are many configurations because any value of s1 is acceptable as long as s2 is fixed here. Yes?
Is it also going to be true that g of n1 plus s1, n1 plus s2, comma s1 plus s2 is equal to that, or the g is not linear? I mean,
No, g is not. G is the g we discussed. Is this g0 e to the minus s squared? We spent a long time discussing. That's the g I have in mind. This is the distribution and the likelihood or the number of states compatible with one value of s1. Everything we said before applies to this and also applies to this. But the total state now is the product of two of those g's that we discussed before. In a minute, I will write them explicitly. Let me leave them as here for a while. So you see that if I want to write all the possible configurations of the system, I have to do a sum here. Because S1 can be 1, and this can be S minus 1, or this can be 2, and this can be S minus 2, or this can be 3. All those are possible configurations, as long as S is fixed. Because that, what did we say? That any possible state compatible with the energy of the system is possible. So all of these configurations are there, and I have to sum over S1. Okay? Because anything that could happen can eventually happen, and these are possible states of the system. So I am not saying that all of them appear with the same proportion. That's what we are going to calculate now. But in principle, they all are there. Let me make a comment about this sum. In general, as you know, S1 runs from minus n1 over 2 to n1 over 2. So in general, those are the limits of this sum, but within the reasonable constraints. Let me give you an example. Let me imagine that n1 is 2000, so I have 2000 spins in one system, and n2 is 10,000. I don't know. And the total number S is 1,000. So there are in total 1,000 more spins up and down. Okay, in that case, yes, S1 can be, remember, in principle, this can run from minus 1,000 to plus 1,000, from minus n1 over 2 to plus n1 over 2. And in fact, in this case, S1 can go all the way from minus 1,000 to plus 1,000, because if this is minus 1,000, this will be 2,000 S2, so that the sum is 1,000. And if this is minus 999, this will be 1,001, and so on. And if this is 0, this will be 1,000, and if this is 1,000, this will be 0, and so on. So in this particular example, yes, N1 can run all, S1 can run all the way from minus 1,000 to 1,000, which is the maximum case. You see, the number of spins up here can be 0, 1, 2, up to 1,000, up to 2,000. But imagine, for example, that I have, what did I pick here? N1 is 2,000, but N2 is only 1,000. And still the total, 1,000, and still the total number of excess spin is 1,000. Well, now you see it's different. S1 cannot be minus 1,000, because if this is minus 1,000, this would have to be 2,000, and there are only, and S2 cannot get that far, because S2 can go up to 500. So obviously here, S1 can go only from 500 to 1,000. That's the whole range. When this is 500, this will be 500. When this is 501, this will be 499, and so on. When this reaches 1,000, this will reach, no, am I doing it right? And 2, if the sum is 1,000, when this is 500, this has to be another 500, which is the maximum value I can have for S2. Okay? When this is 501, etc. When this reaches 1,000, this will reach 0. Okay, so that's the limit. So in this case, my sum over S1 will not run from minus 1,000 to 1,000. It will run only from 500 to 1,000. But whatever, in each situation, you will have to analyze the limit. But the point I am making is that all these are possible states of the system, and if I am doing a calculation, I would have, in principle, to calculate all these possible states and sum over all of them, because all of them are possible states of my system. This function I know, this function I know, but I would have to sum. What I want to show you is that in reality, particularly for very big numbers, this doesn't happen, that this sum is such that is completely dominated by one term. There is the maximum of this, the maximum value of this sum, the maximum value of S1, the one that makes this term the maximum, that is much, much bigger than all the others. And so when you are doing a statistical analysis, you might as well forget that you have a sum and you concentrate on the term that is like that, because the system is overwhelmingly likely to be in that case. That's what I want to convince you about. So let me see if I can go around now and actually start convincing you. So what I am saying is that there will be a certain value of S1, which I will call, I am following the notation of Kittel, S1 maximum, and corresponding to it an S2 maximum, which will be S minus S1 maximum. So there will be one value of all the ones in the sum, which will be the biggest. That's obvious. You have a sum, there is some number that will be bigger than the other, but I want to convince you that any other number is much, much smaller than it. So that's what I am trying to convince you. So first of all, let me evaluate what that number is. Okay, first of all, I want to evaluate that number. So let me write the generic term, N1 of S1 and the G2 of N2 of S2. This is the generic term. I want to see of all these terms which one is the biggest. This is by definition, if you remember, this is the G1 of 0, of S1 equals to 0, times e to the minus 2 S1 squared over N1 times the G2 of 0 e to the minus 2 S2 squared over N2. Okay? That was our G's that we calculated before.
Are they both S1, G2 and 2 S1?
No, this is S1, this is S2. Yes, but of course S2 has to be in the sum S minus S1. So if you want, we might as well put it, because remember, the only terms that contribute is when S2 is exactly S minus S1. So there you have the expression in terms of S1, and I want to find which value of S1 makes this expression the biggest. Okay? So the easiest thing, instead of taking the derivative and equating to 0, which is what you would do, is look at the logarithm. Normally, when you have exponentials, take the logarithm. Logarithm is increasing. So if I find which expression maximizes the logarithm, I can then exponentiate again. So if I take log, I get ln of G1 of 0, G2 of 0, which, remember, this was square root of 2 pi and 1. The point is that it doesn't contain the letter s. minus 2s1 squared over n1 minus 2s minus s1 squared over n2. Did I write it right? Yes. So that's the logarithm of that quantity, and I want to maximize it, so I want to take the derivative of this with respect to s1 and equate it to 0, which is very easy. This doesn't matter. This is minus 4 s1 squared, s1 over n1, sorry, minus plus 4 s minus s1 over n2. The plus because there is a minus here. Okay? So, and this should be equal to 0 to maximize that expression. And indeed, that tells me that s minus s, sorry. Okay. That s minus s1 over n2 has to be equal to s1 over n1. Okay, by the way, let me, as an auxiliary thing, this is the condition of maximum, okay? To make sure that this is a maximum and not a minimum or something strange, some inflection point, I will take one more derivative, because the second derivative has to be negative if I am in a maximum. And this is minus 4 over n1 minus 4 over s2. Correct? Because when I take the derivative, I get a minus 1 here and I get a 1 here. This is clearly a negative number, so means that the first derivative corresponds to a maximum. So this is the condition that will give me a maximum value of my term. And so if you look, means that s1 over n1 has to be equal to s2 over n2. When I am at the maximum, which I denoted with a little hat, is when the proportion of spins down the excess spin in one system, or the fraction of excess spin in one system, coincides with the fraction in the other system. In other words, if the whole system has 70% of the spins up, the maximum will not correspond to 68 here and 63 here, will correspond to exactly 70 and 70, when each one of the two subsystems has exactly the total fraction. Okay, so this will correspond to the maximum, and this is, of course, S over N.
This is the maximum of a system where it's maximum spin up.
The maximum, the value in that long sum when I would get the maximum number of states. This was a sum over many values of S1. I was trying to find which S1 will give me the biggest term in that sum. And it turns when this is equal to that. In other words, if the total fractions of spin here is 10%, it will be when that system has an excess of 10% and this one also. Not when that one has 12 and this one has 8, or that one has 17 and this one has 3. It's when both have exactly the same fraction, given by the initial state of the system. Okay, so this is the important thing for the time being. And not only that, so it's not important to identify the biggest term. What I need to know is that the other terms compared to these are small. So now I want to write another term to compare. So, in other words, let me write the biggest term in the sum. So G.
What is maximized?
The term, the product, G and G1.
So that's the states, the amount of states?
The state is a sum of many terms. I am trying to see which one of those terms is the biggest. Because I will show you that all the others are so small that essentially when you see that sum, forget about that and just pick the biggest term.
So the most the state with the most spins out.
The most probable.
No, not the state with the most spins up. My system was prepared that the number of spins up, I tell you, I will have a system that has exactly 83% of the spins up.
Oh, which state?
But which particular of all the states with 83% up is the one that is the biggest? Because we said that we can have in this state, if the total number of spin is 83, it can be 87 and 72 or 89, whatever. I showed you that the biggest in all those terms in this long sum that is here is precisely, of all this sum, the term when it's exactly 83 and 83 in both sides, that's the biggest of all this sum. What I want to do now is to write that term to be able to compare it with the other terms in the sum, to convince you that the others are much smaller. That this is the biggest, we know because we took a derivative. But that the others are smaller, I want to show you. So what I will have is my first term is Gn1 S1, I am calculating at the maximum, times G1, G1, G2 of N2, S2 maximum. I am calculating the maximum. And this will be G1 of 0, G2 of 0, e to the minus 2 S1 maximum square over N1 minus 2 S2 maximum square over N2. That's by definition. I replaced S1 and S2 by the maximum value. But now let me do the following. Let me show you this is the same as writing G1 of 0, G2 of 0, e to the minus S1 square over N1 square N1 minus 2 S2 square over N2 square N2. Okay? I just multiply and divide by something. But now we know that this number and this number are the same. S1 over N1, which appeared here to the power 2, and S2 over N2 are the same, and they are just minus S squared over N squared. We said that this is S over N times N1 plus N2. G1 of 0, G2 of 0, and this is G1 of 0, G2 of 0, e to the minus 2 S squared over N. That's the biggest term in the sum. Okay? So now we have identified, and how does it depend on the total S of the system. So I want to now calculate a different term in the sum to compare it with it. Okay? And so I will consider, for example, the case when S1 is the maximum plus delta, where delta is some small number, and S2 is S2 minus delta. Remember, S1 plus S2 has to always be S1 hat plus S2 hat. So if this one differs by an amount delta, this has to differ by an amount minus delta, whatever delta is. Okay? So let me calculate it. I will do it for a general delta. Delta can be 1 or can be a billion, I don't care. So this term will be G1 0, G2 0, and I will get e to the minus 2 S1 plus delta squared over N1 minus 2 S2 minus delta square over N2. Okay? We said that the general term is given by this. But you see that when I take the square of this and the square of this, that will give me, again, the biggest term in the sum. So I will have here G1 of 0, G2 of 0, e to the minus S squared over n, because this one will be S squared, but by the same reason I gave you before, but I still have all the terms that I didn't include. E to the minus 2, what do I have? 2 S1 delta over n1, e to the minus 2 delta square over n1, coming from the other two terms, e to the minus 2, I have a minus, plus s2 delta over n2, e to the minus delta square over n2. What I wrote is, I open this and the quadratic terms go here, because that is the biggest term, and this is how much this differs, okay? So, and you see, the main point is that this term and this term cancel. This is e to the minus 4, if you want, s hat, s1 hat over n1 delta, and this is e to the plus s2 hat over n2 delta, and remember these two things are equal. So the main point is that this term and this term go away, and what I have is that what I get is the maximum term, I will call it like this, G1, G2 maximum, the biggest of all of them, multiplied by e to the minus 2 delta square, 1 over n1 plus 1 over n2. This is by how much my term differs from the biggest one. So now at least I can calculate something. So let me do some reasonable numbers. N1, I will assume, is 10 to the 22. Okay, I am considering a real system. Delta 1 and N2 the same. So I'm considering that my two systems are really macroscopic systems, so it's something like a liter of something with a big number. And delta, I will consider that is as big as 10 to the 12. You will see why I picked 10 to the 12. But the point is that if delta is 10 to the 12, 10 to the 12 is 1 in 10 billionth of 10 to the 22. So I am assuming that instead of having the maximum term, I have a term in which one spin every 10 billionth of the remaining spins doesn't point the right way. So I have the biggest term and one term in which one spin in 10 billion, whatever that is, points the right way. So just look at this factor. This is e to the minus 2, 10 to the 24, which is delta squared, divided this 1 over 10 to the 22 plus 1 over 10 to the 22 is 2 over 10 to the 22. How much is that? Is e to the minus 400. Okay? So the term that contains one spin in a billion not being at the maximum has this probability, or it is this much smaller than the other term. This number, for your instruction, is around 10 to the minus 174. This is how likely it is that instead of having the biggest of all the terms, you have a term in which one spin in every billion points the wrong way. So you can make a real objection here. You say, well, yes, this is the same as calculating what is the probability that this particular spin points the wrong way. But you see, what is, instead of being 10 to the 12, there are 10 to the 13, and 10 to the 14, and 10 to the 15. So if I want to know what is the likelihood of a fluctuation this big, in reality I would need to sum all the values of delta going from 10 to the 12 on, because that would give me the possibility that I have in a fluctuation which is one spin in I said a billion, 1 in 10 billion, right? This is 10 to the minus 10. So that would be how likely it is to have a fluctuation in which 1 in 10 billion spins or more are pointing the right way, which will be a little bigger than this. But you know, how much bigger is it? So this is the likelihood of having 1 spin in 10 billion. Now let me consider 2 spin in 10 billion. Well, it will be even a smaller number, but let me assume it's the same number. Let me consider 3 spin in 10 billion. Will be another number like this, okay? So let me sum all the numbers starting from 10 to the 12 and going all the way to 10 to the 22. And we'll assume that all of them are as big as this one. In reality, they will be becoming smaller and smaller and smaller. But just for the sake of argument, let me assume that they are all like that. How many numbers are between 10 to the 12 and 10 to the 22? 10 to the 22, okay? Because it's 10 to the 22 minus, you know, how many numbers are between a million minus 10, between 10 and a million, essentially a million, you know, 990. So roughly speaking, multiply 10 to the minus 172 times 10 to the 22 times n, okay? Because there are n states. Well, there are a few that I'm not counting, but let me give them to you. It will be 10 to the 22 minus, will be 10 to the 21.99999 with 9 zeros. How much is that? It's 10 to the minus 152. Still is a very small number. So the probability that you will hit a state which differs from the biggest state in that sum by more than 1 spin in a billion is 10 to the minus 152. This is what Boltzmann called zero. Okay, you can say, well, it's not zero, it's some number, but what Boltzmann said is, imagine that you have, your state goes to all possible states, and every instant it changes and go from one to the other, and they are all equally likely, because we said that all states are equally likely. The state with there is a big fluctuation, a small fluctuation, but what is the chance that you will find this one? Well, it depends. You know, you did the problems in probability. The likelihood of something very small might not be that small if you do many trials. You calculated that. The problem of the supernova, for those of you who did it, the probability of the event that I mentioned happening was 10 to the minus 6. But since you were running the experiment for many hours, well, the total probability ended up being 25%. So you can say, well, my system has a very small chance of being in that strange state. But, you know, as the time goes on, it's trying all the states. So let me imagine being extremely generous that in every second it goes through a billion states. Let me be more general. Let me try to assume that it goes through a trillion states. So in every second, you try 10 to the 12 configurations of your system. And you keep going. Okay? So if 10 to the 12 is that number, well, to hit this, you would need to wait 10 to the 140 seconds, right? To get a chance of hitting this. If you try 10 to the 12 every second, and the probability of this is 10 to the minus 152, you know, you will get 10 to the minus 140. So you will have to spend this amount of time till, on average, you will get one of those configurations. This, for your information, is 10 to 134 years. I don't know what chronology you want to use and what you want to consider the age of the universe, but if you do the normal chronology, it's 10 to the 13 seconds, the age of the universe. You see, when Boltzmann said never, he meant never. You say, you can spend the life of the universe, and your system can go to all the states, but you will never find a state which will be differing from the maximum by a part in a billion. So will you find a state that differs from the maximum in 1, that has all the spins exactly as they should be minus 1? Yeah, of course, that will happen. You know, this is the same as saying, well, If I flip 100 coins, you know, it's not always I will get 50, sometimes I will get 51. But you see, if I ask you, will you get 99? How many times would you have to flip a coin, assuming it's a fair coin, to find a run of 100 flips with 99 heads? Well, you will do the calculation and you will see that it's longer than the age of the universe. So in that sense, we say never. So you see, we are not saying never, never in the sense that this can never happen. We are saying, yes, it can happen, but it cannot happen. I will give you another example in a minute that goes to the heart of that in a second. But, well, let me do it now. Let me give you, and I was saving this for later, but normally when we discuss entropy, but let me assume, and probably today, if not today, next class, we are going to start discussing the distribution of molecules in this room, the famous Maxwell-Boltzmann distribution. The velocity, the molecules of nitrogen and oxygen in this room are moving with varying velocities. So you agree with me that if I pick one molecule and I paint it red and that molecule is moving around, is as likely to be in this half of the room than in that half of the room, right?
Yes.
So you pick another molecule also, and you pick another molecule also. For each molecule, it might be come on, man. You pick a molecule, the molecule has a chance of being here or here. You pick another molecule, the same. So how many states does your system have? 2 to the n, right? Well, it's the same as the spins. There are 2 to the n configurations. One configuration with all the molecules here and none here. N configurations with n minus 1 molecule here and 1 here, because it's a combinatorial n1, etc. It's the same problem, thinking in another way. But, you know, it's the same problem, where n is a big number, 10 to the 22 precisely. So that means that among all the configurations, of course, there will be the configuration which has the biggest probability in which the molecules are 50-50. Because you know that that's the combinatorial n over 2, right? The number of ways in which you get 50-50. In other words, the density in the left half of the room is equal to the density in the right half of the room. But in principle, any configuration is, according to what I am developing here, as likely as the other. So among the configurations, the configuration in which all the molecules in the room happen to be in that half, and none in your half, and there are in my half, is a possible configuration. It's there. Among the 2 to the n is as likely as any other. What would happen if we sample that particular configuration? Well, I am in this half of the room, so the amount of oxygen that will be getting to my brain will be twice as normal, because the richness of oxygen in the air will be twice as big. So I will be getting my bloodstream a little higher. I will get a high, I will speak faster than usual, I will be very excited. What will happen with you? You will die. If there are no molecules in your side of the room, you cannot survive. So among all the possible 2 to the n configurations, the configuration in which I am sillier than usual and you die is there. Of course, the other one is also as well, in which you are the silly and I die. That's also fair game. You see, still you don't panic. You are not saying, oh boy, will this be an unlucky day and will I die because all the molecules that are as likely as being here or there will all be here? No, because you know that that configuration has a probability 1 over 2 to the n, and this one has a possibility much bigger. So it's not that one configuration, there is nothing in the law of physics that says that the molecules have to be divided 50-50, except the fact that it's more likely. But among all the possible physical states, the state where all the molecules are in one half of the room and none are in the other is there. The fact that we never observe it which by the way, that's the content of the second law of thermodynamics, is simply saying that whatever is more likely to happen than whatever is less likely. Okay? Yeah, it's a tautology, but that is the case. But it's a tautology that we live with. We assume always that if you have, now let me do it physically. You take this container, you evacuate 1/2, and so that the density here is whatever, 10, and then you open a valve between them, you don't assume that you will get 9 and 1. You know that you will always get 5 and 5. And you will never again see that you have 10 here and 0 here. You know that those laws work, okay? All I'm trying to show you is that these are laws of statistics, and these are not anything, because given a certain molecule, we will calculate. Next class, what is the probability of a molecule moving to the right and to the left? You will see it's the same. So that the molecule is here or there, the chances are 50-50. It's only that when you have n of them, certain laws appear. So that's the point I'm trying to make. There are certain states that dominate the statistics. In the case of our sum, although the sum is very big, this sum that we have G of N1, S1, G of N2, S2, and I have to sum over all possible S1s, but when you sum, there will be one state that will be so big compared to all the other ones that when you are trying to do statistics, you might as well consider that the system is in that state and that's it. And you do statistics on that state alone, because that dominates so much the other ones. So now I want to generalize all the things I said for spins to a general system. Forget about spins. I have two systems, energy U1, energy U2. They exchange energy. Let me see what happens. So this was just to motivate you, but now we'll do it and we'll get the definition. Thank you. The statistical quantities that we care, okay? So I am assuming, now let me do it in general. Forget about spins. I have a system that has n degrees of freedom, has total energy U, and as I mentioned, if I obtain, this system has two parts, one with energy U1 and one with energy U2, the number of states of the system will be G1 of N1 U1 multiplied by G2 of N2 U minus U1, because the total system might have energy U. I am calculating the probability that my system has energy U. Sum over all values of U1. So now I'm doing it in general. I'm forgetting where U1 is some number smaller than U. Let's assume that my system cannot have negative energies, okay? So G2 can have any number between 0 and whatever, G1 the same, but if the total energy is U, U1 can have any value between 0 and U. If it goes to minus infinity, it goes minus infinity. It doesn't affect for the argument. But I am generalizing what I said before, only thinking in terms of energy. And what will happen here is simply that in all this sum, there will be one term that will dominate completely the sum and will be the maximum one. And which one is it? Well, now I have to calculate it in terms of this. So I want to calculate the term. So how will, in other words, how will the energy be split? What will be the fraction in part 1 and what will the fraction in part 2? Okay, well, the answer is the term that makes all this sum the biggest. Of all these possible terms corresponding to U1 equal to 0, 1, 2, 3, whatever, the one that makes this the biggest. So let me calculate the change. Let me do it now in general. What will be the change in the number of states when I have a certain amount of energy U1 This has U1, this has U2. Let me see. The total energy is U. The system is isolated. So see that I am just generalizing what I said before. And let me calculate how will a particular state change when a certain amount of energy goes from here to here. So I will have a certain change, du1, for this energy. And of course, I will have a corresponding change du2, but du1 plus du2 has to be equal to 0. The system is isolated, so if this loses 3 joules, this has to gain 3 joules, or vice versa. Okay? So I want to consider how this changes when there is a change u1 and u2, of course, in this quantity u2, subject to the condition that du1 plus du2 has to be 0, which is saying that the system is isolated. Well, the change of that is I have to calculate in this sum the derivative, right? And I have to calculate what is the derivative of that. This will be the derivative of g1 respect to u1, keeping n1 fixed. g1 is a function of two variables, n1 and u1. So I take the derivative respect to u1, keeping n1 fixed. I am assuming that molecules, in this case, cannot move. It's only energy that can move. du1 times g2, sorry. So let me do it correctly. Times g2 du1 plus, I will leave myself room, but then the other term will be g1 times the derivative of g2 respect to u2, keeping n2 fixed, du2. Okay? This will be the change in this system when there is a change in the energy u1 here and a change in the energy u2 there. Okay? It's the sum of this plus this. I took the product and I derived in each term. Only that I will apply the condition that du1 and du2 have to be equal and opposite to each other. Because if one loses 3 joules, the other has to gain them. This is an isolated system. Okay? So if this is going to be equal to 0, there is one way and only one way in which this can happen. If dg1 with respect to u1 at constant n1 times g2 is equal to dg2 with respect to u2 at constant n2 g1. Okay, because du2 is equal to minus du1, so this minus this is equal to 0, or this is equal to this. So the condition that maximizes G is this one. Well, this is a generalization in a more abstract language of everything I said counting spins. And G1 and G2 are whatever describes my system 1 and my system 2. Need not be spins, is whatever. But every system is characterized by a certain function that tells me how many states are there for a certain energy. Okay? Whatever that function is, which in the case of spins we learn how to calculate it, in another systems I don't know, but whatever it is, this is the condition that will give me the maximum term. Okay? And, yes?
Can you explain again why there's no negative sign?
Because du2 is minus du1. The energy is conserved. So if du1 is some number, du2 is minus that number. That's where I get that, because the total change in energy, du1 plus du2 has to be 0. Energy cannot change, escape my system. Okay, and look at this. If you divide by g1 and g2, you get 1 over g1 dg1 du1 at constant n1 is equal to 1 over g2 dg2 at constant respect to U2 at constant N2. Later on, we'll see that if the number of states depend not only on N and U, but depends on 5 more variables, well, U derive respect to U, keeping all the others constant. And we will do that later. But for the time being, I am assuming that the only interesting parameter besides the energy on which G depends is in the number of particles. But if there are more, volume, many other things will appear later. For the time being, I am not complicating. And this is the same as saying the derivative of ln of G1 respect to U1 is equal at constant N1 is the derivative of the ln of G2 with respect to U2 at constant N2. That's the condition of a system in equilibrium. This has to happen for a system to be in equilibrium. That the rate at which G1 or its logarithm is changing with the energy should exactly match the rate at which G2 or its logarithm is changing with the energy. Now definition comes Mr. Boltzmann, and he said the logarithm of G1, I will call it the entropy of the state. The entropy of a state is just the logarithm of G, of the number of states. So sigma entropy. I don't call it S as you called it in elementary physics because I am so far it's not exactly the same. See, G is a number. So the logarithm of G is a number. This has no units. The entropy you learned late had units of joule per degree or something like this. But this is very similar to the entropy, but that's the way Boltzmann called it. So my conclusion is that the condition of equilibrium is that the derivative of the entropy of state 1 with respect to the energy 1 has to be equal to the derivative of the entropy of state of system 2 with respect to U2. When two states, 1 and 2, are put in contact, energy will flow between them until this happens. The change in the entropy of one of them with respect to the energy matches exactly the change of the entropy of the other with respect to the energy. Okay? That's the condition of equilibrium between states, called by Mr. Boltzmann. Okay? So, if you want to make connection with what you might have learned in physics, what is the condition of equilibrium between two states? We know what it is. That's, you call it zeroth law of physics, zeroth law of thermodynamics, or whatever. Two systems will be in equilibrium with each other when their temperatures are the same. Okay? And if one is hotter than the other, energy will flow. The energy will not flow anymore when they have the same temperature. So what suggests here is that, and this is the mental step through which Boltzmann went, he said this quantity somehow has to be connected to the temperature of the system. Okay, this quantity, the change in the number of states, or the logarithm of the number of states with respect to the energy, somehow is the parameter that determines the energy of this, determines the equilibrium of the system, and is related to what people from 100 years ago have been calling the temperature of a system. Two systems are in equilibrium when they have the same temperature. So I could have called this the temperature. They didn't. For reasons that will become clear, they call this 1 over the temperature. So they define this sigma du as 1 over tau, and that's the tau that sometimes we call the absolute temperature. Why absolute? Because, check, this has units of inverse energy. Okay, it's the derivative of a number respect to an energy. So this is measured in inverse joule. So this temperature is not measured in degrees, it's measured in inverse joule. Okay, but it's another name is the absolute temperature. if you want to connect it with what you learned in kindergarten with the temperature, well, then this will be what you call 1 over kT, where K is the Boltzmann constant, which is joules per degree, and you multiply by a temperature and you get joules. Okay, this is energy per unit of temperature, and you multiply by a temperature and you get inverse energy. Where does this constant come? We'll learn. We will discuss kinetic theory and we will see where this constant comes, but for the time being it's a constant that establishes the connection between the microscopic and the macroscopic world, because temperature is what you measure with the thermometer in our real world, and this comes from counting microscopic states. So you can write these two expressions the same way. This sigma, let me write it in the two ways or in the way that it's more familiar. This sigma du is equal to 1 over K Boltzmann T. So this is my definition, and this is the temperature measured in the Fahrenheit scale of temperatures, and we'll go through how this is derived, etc. Or you can put the constant there and say that the derivative of K sigma, you move the constant there, K sigma respect to U is 1 over the temperature. So K sigma now is an entropy measured in units. This was a number. This is measured in joules per degree. This is the entropy you learned in physics 3. So this is ds du equal 1 over T. And S is the old entropy. So you see, the entropy that people had been using for 60 years by the time Boltzmann got into the problem is K times sigma, or K Boltzmann now times sigma, K times the logarithm of the number of states. Okay, so this is the definition of entropy. If you want to convince yourself that this is an important formula, or well, perhaps I shouldn't say that. If you want to convince yourself that Boltzmann thought it was an important formula, just Google any of you Boltzmann, or Google Boltzmann's grave. You will see in his the cemetery in Vienna where his grave is. This is what it says, the grave. So he considered this his biggest insight, and probably it was. It's one of the most important things, because this connected a quantity that people have been using for 100 or 70 years, just defining the efficiency of a machine and what happens with vapor goes into a machine. We will go through all of that, and that's what you go in elementary thermodynamics, I'm sure. So some of you are familiar, and some of you will find it later. But he connected that with the microscopic world of counting states. And he said, entropy is just a measure of the number of states. So saying that a state has more entropy is saying simply that it's more likely than other states. States that have more entropy are more likely, have a higher probability or a higher number of states associated with them. Okay? So if you found the picture, show it to everybody, or show it in a few minutes. We'll break in 2 minutes, so you can show it. I was going to bring a picture and I forgot. Or perhaps I did. Okay? So I am making the connection, but for us, because the book by Kittel doesn't want to get into these details first, he wants to treat it as in general, he uses the expression, the sigma du, where you calculate how the number of states changes with energy when everything else remains constant. In our case, it's just the number of particles. But if you have a system that depends on many more variables, if sigma is a function of u, n, the volume, some magnetic field, well, you change sigma with respect to u, keeping everything constant. That's what we associate with the temperature. I'll comment later, perhaps after the break, why we use the logarithm and not g. What is the advantage of that? besides the fact that I told you already that when numbers are big, the logarithms are a little smaller, but you will see that it has some physical reasons why you want the logarithm there. Why you want this the inverse? Well, you could have defined the temperature as this. And the temperature will, instead of having units of energy as it has here the temperature is measured in joules, okay? The sigma du is 1 over joule, and 1 over tau is 1 over joule. So here we have a temperature measured in joules. Normally we have this constant, which is joule per degree times T. So our temperature is energy over energy per degree, which is degrees. But the question why we define 1 over T and not tau, it's a matter of practicity. You will see that we like to think that when heat flows from body A to body B, body A is hot, has a higher temperature than body B. If we had defined this as temperature, we would have found that when energy flows from body A to body B, body A has a smaller temperature. And that sounds counterintuitive, so they chose to define it like this. But we could have defined the world and everything would have been fine if we choose a definition in which this would be tau. Doesn't matter too much. You will see that the mathematics later will become simpler with having the T defined like this. But perhaps just to finish, let me point one very simple thing, because then it will be a very good point to stop. Let me point the following. Now let me see what is it that we learned. That if we have two systems, this is characterized by energy U1 and tau parameter, where tau is what I just defined, the change in the logarithm of the number of states with respect to U. This is characterized by tau1, and this is a U2, and is characterized by a parameter T2, where a tau2, where the taus are exactly what I defined here. Is the rate of change of the logarithm of the number of states with respect to the energy, okay? So this system has a certain parameter, this system has a certain parameter, I put them in contact. The question is, will the energy go from here to here, or will the energy flow from here to here, or not at all? What will happen? So now we can answer that very simple. Well, when I put them together, because, remember, G is the product of the number of states here times the number of states here, G is a product, because if this can be in 10 states and this can be in 30, the whole system can be in 10 times 30, 300. The logarithm of G, since G is G1 times G2, the logarithm of G is the logarithm of G1 plus the logarithm of G2, or the entropy of the whole system is the entropy of part 1 plus the entropy of part 2, okay? So you see already one of the reasons why I want a logarithm there, because then entropy is an additive quantity. If this has entropy 1 and this has entropy 2, the whole system has entropy 1 plus 2. Okay? So let me calculate how does sigma change when energy flows. Let me assume a certain amount of energy delta U flows from here to here. Let me see what happens to sigma. Well, you will agree with me that the change in sigma is the change in sigma 1 plus the change in sigma 2. So the total change in sigma will be the derivative of sigma 1 with respect to U1, keeping constant N1, times delta U1, plus the derivative of sigma 2 with respect to U2, keeping constant N2, because I don't let the particles move, delta U2. That's the total change in sigma when there is a change delta U1 here and I change delta U2 here. But of course, I am going to use that delta U2 is minus delta U1. And the system energy is conserved, so whatever one loses, the other gains. So I might as well write, since energy, I am saying, flows from here to here, the delta U1 will be negative. This system is losing energy, this is gaining in this particular case, because they put this arrow. So this I will call minus delta U, and this plus delta U. In this case, I want to analyze what are the conditions for energy going from the left to the right. Okay, so what do I get? Minus the derivative of sigma 1 with respect to U1 plus derivative of sigma 2 with respect to U2. This is at N1 plus N2 multiplied by delta U. That's the total change in entropy. Okay? Because these I replaced by minus delta U and this by delta U. And, oops. I went too far. I already missed my punchline. Move me back, please. Just one click. Okay, good. So this is minus 1 over tau 1 plus 1 over tau 2 delta U. So the change in entropy is precisely this amount. So there you have it. When will the change in entropy be positive? Delta U is a positive number, right? When all this number is positive. In other words, when this is smaller than this. Okay, when tau 1 is bigger than tau 2. If tau 1 is bigger than tau 2, moving energy from system 1 to system 2 increases the entropy of the system. If tau 1 is smaller than tau 2, this number dominates over this one, this is negative, and moving energy from system 1 to system 2, it decreases the entropy. So the flow of energy will be that way if this system has a bigger tau than this system. Okay? So that's why in our world, when you put in contact a hot body and a cold body, heat flows from the hot body to the cold body. It doesn't flow from the biggest to the smallest or any such thing. You put a hot little piece of iron in the middle of the ocean, although the ocean has obviously much more energy than the iron, energy will flow from the iron to the ocean. But if you put, I don't know, a little piece of an ice cube in the ocean, energy will flow from the ocean to the ice cube. Okay? Energy, because the entropy, the system goes to states of more probability. If all systems are equivalent, the system will go to the state where the system is more likely to stay. And that happens when energy flows from the system with bigger temperature to the system of lower temperature. Okay? So the famous law, and this is in essence, I am explaining in a very layman's way, the second law of thermodynamics. When you put two systems in contact, the flow of energy will be such that the system will tend to go to the state where it is more likely to be. Okay? And it is more likely, as I showed you here, when energy leaves the system that has bigger temperature and goes to the system with lower temperature, and not the other way around. If energy goes from here to here, the states go of a state of higher probability to a state of lower probability. Can happen? Yes, if you wait a gazillion years might happen, but in practical terms, each time that I put a little ice cube in my scotch, I know that it will melt and not the other way around. It's not going to be that the water will start boiling somehow and the ice becoming colder. Doesn't happen. So the temperature of the water goes down and the temperature of the ice goes up. But that's a statistical process. The laws of physics allow both, because as long as the energy that one loses, the other gains, conservation of energy is satisfied, and that's all we ask in physics. That if we have two systems and one loses 10, the other should gain 10. That's all we want. But the fact is that it's more likely that this is the one that loses and this is the one that gains. So that's the content of the second law. So in some sense, now I am ready to establish the laws of thermodynamics the way you learned it in Physics 1. And you will see it will take me 10 minutes now to establish the laws in those terms. Of course, we will go to thermodynamics later and discuss this in much more detail and extract consequences. But in principle, the statements of the laws is all here. You know, what I already discussed today, we have all the three laws, or if you count the zeroth law, the fourth laws of thermodynamics are here. And I will do that immediately after the break. So I'm stopping here. Okay. Good.